Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the amplitude modulation. Now if you have followed the previous video on the double sideband suppressed carrier, then you must be aware that this modulation scheme requires the synchronous or the coherent demodulation. That means for the demodulation at the receiver end, the phase and the frequency of the locally generated carrier signal should match with the modulated carrier signal, which not only increases the cost but also increases the complexity of the receiver. So this type of complexity and the cost is alright for the point-to-point communication. But in case of the broadcasting system, the receiver needs to be simple and the cost effective. Because in case of the broadcasting system, one station transmits the signal and several hundreds or thousands receive the same signal. So the receiver needs to be simple and the cost effective. And we had seen that it is possible to achieve that if we just send the carrier signal along with the DSBSC signal. So this modulation scheme is conventionally known as the amplitude modulation. And even it is known as the double sideband with carrier or the double sideband with full carrier. Now if you see this expression, then further it can be written like this, right? It means that to generate this AM signal, we just need to add some DC offset to this message signal. So in case of the DSBSC, to generate the modulated signal, the message signal is multiplied with the carrier signal. While in case of this amplitude modulation, first of all some offset is added to this message signal and then it is multiplied with the carrier signal. So we will see different generation techniques in the separate video. But this is how this AM signal can be visualized. Now if this offset is 0, then it is the DSBSC signal. But when we add some offset to this message signal, then it will get shifted upwards by some amount. But this offset should be added in such a way that there is no zero crossing of the message signal. Or in other words, this AC plus MT should be greater than or equal to 0. Because if you are aware, in case of the DSBSC, every time there is a zero crossing of this message signal, then there is a phase reversal in the modulated signal. But somehow, if we can avoid that, then the demodulation of this AM signal will become very simple. So we will see that how it will become very simple. But for a moment, just keep this thing in mind. That means for this asynchronous demodulation of this AM signal, this AC plus MT should be greater than or equal to 0. So that we can avoid the zero crossing and eventually we can avoid the phase reversal. So considering this condition is already satisfying, let us see the modulated output. So this AC plus MT will get multiplied with the carrier signal. And if you see the modulated output, then it can be represented by this yellow signal. So here, this plus minus AC plus MT is the envelope of the modulated signal. That means we can say that this modulated signal contains within this envelope. Now this envelope is not part of the modulated signal. But at the receiver, somehow if we can generate this envelope from this modulated signal, then it is possible to recover the message signal from this envelope. Because if you see the shape of this envelope, then it follows the message signal. And just by blocking this DC term, it is possible to recover the message signal. So this technique is known as the envelope detection. So in this technique, the modulated output is first passed through the rectifier. And this rectifier allows only the positive side of the modulated signal. And passing this signal through the RC filter, it is possible to recover the envelope. But this envelope detection works when this A plus MT is greater than or equal to 0. That means the first condition for this envelope detection is AC plus MT should be always greater than or equal to 0. Then the second condition is the carrier frequency FC should be much higher than the modulating frequency. Or in other words, we can say that this carrier frequency should be much higher than the maximum frequency in the message signal. So we will see this envelope detection technique in the separate video. But if this AC plus MT is less than 0, then there will be a zero crossing. And because of that, there will be a phase reversal at every zero crossing. So in this condition, if we try to recover the message signal using the envelope detection, then we would get this kind of signal. And certainly this is not the message signal, right? That means whenever this condition does not get satisfied, then there will be a distortion in the output. So to avoid such distortion, this envelope signal, that is AC plus empty, should be always greater than or equal to 0. Now this same phenomenon can also be explained in a better way using the term which is known as the modulation index. And sometimes it is also known as the modulation depth. So this modulation index defines to what extent the carrier signal gets modulated by this message signal. And to understand it, let us take the example of the tone modulation, where the message signal contains only a single frequency. So let's say the message signal frequency is equal to FM and the carrier frequency is equal to FC, and the amplitude of the carrier signal is varying between the AC and the minus AC. So as we have discussed, after the modulation we will get this yellow signal. So for the sinusoidal signal or for the tone modulation, this modulation index mu can be given as AM divided by AC. That is the maximum amplitude of the message signal to the carrier signal. And if we relate it with our previous discussion, then here the minimum amplitude of this message signal is equal to minus AM, right? So to avoid the zero crossing, this carrier signal amplitude should be greater than or equal to minus AM. Or in general we can say that this AC should be greater than or equal to AM. And we know that this modulation index is equal to AM divided by AC. So from this we can say that to avoid the zero crossing, this modulation index should be less than or equal to 1. That means to recover the message signal using this envelope detection and to avoid the signal distortion, this modulation index should be less than or equal to 1. So in this modulated signal, this modulation index is between 0 and 1. Then if we see in this second case, then here this modulation index is greater than 1, or we can say that it is the case of the overmodulation. So in this case, it is not possible to recover the message signal. Now in the third case, this carrier signal is unmodulated, or we can say that in this case, this modulation index is equal to 0. And this is the fourth case where the modulation index is equal to 1. That means in this case, the amplitude of the message signal and the carrier signals are equal. That means in this case, AM is equal to AC. Now there is another expression for this modulation index, and this expression can be used for any type of message signal, or we can say that it is the general expression. So if you observe this modulated output on the CRO, then quickly we can find the modulation index using this method. So let us see that expression. Now if you see this modulated signal, then at this point the amplitude is equal to AC, because from this point onwards the message signal is starting, right? Now the message signal amplitude can go maximum up to the AM. That means at this point the amplitude will be equal to AC plus AM. And in fact at this point the amplitude of the envelope will be also maximum. So we can say that the maximum amplitude of the envelope, that is Emax, is equal to AC plus AM. Now this message signal is varying between AM and the minus AM. So this shows the peak to peak value of the message signal. That means at this point the amplitude of the modulated signal will be equal to AC minus AM, and that will be also the minimum value of the envelope. So we can say that this E minimum is equal to AC minus AM. That is the minimum value of the envelope. And if we just solve these two expressions, then we can find the value of the AC and AM in terms of the Emax and the E minimum. That means AC is equal to E maximum plus E minimum divided by 2. Similarly, this AM can be written as E maximum minus E minimum divided by 2. Now we know that this modulation index can be given as AM divided by AC. So from these two expressions we can say that this modulation index is equal to E maximum minus E minimum divided by E maximum plus E minimum. So that is a generalized expression for the modulation index. And this expression can be used even if the signal is asymmetric or has some non-zero offset. So the same expression can also be written as A maximum minus A minimum divided by 2AC plus A maximum plus A minimum, where this A maximum and the A minimum are the maximum and the minimum values of the message signal. And this particular expression will be very useful when the message signal is asymmetric or has some non-zero offset. So let us quickly see that how we can get this expression. Now here if you closely observe, then this E max minus E minimum is basically a peak-to-peak value of the message signal. So if the message signal is asymmetric, then in that case this E max minus E minimum will be equal to A max minus A minimum, right? That means the numerator will be equal to A maximum minus A minimum. Now in the denominator we have a E max plus E minimum. Now if the message signal is asymmetric, then the E maximum will be equal to AC plus A max. Similarly, this E minimum will be equal to AC plus A minimum. So from this we can say that the modulation index is equal to A max minus A minimum divided by 2AC plus A maximum plus A minimum. So this is the generalized expression for the modulation index. Alright, so now let us take the case of the multitone modulation, where the message signal contains a sinusoidal signals of more than one frequency. So here let's say this M1t is equal to AM1 times cos of 2 pi FM1 times t. Similarly, this M2t is equal to AM2 times cos of 2 pi FM2 times t. So here basically we are taking the case of the two-tone modulation. That means the message signal contains the two sinusoidal signals. So from this we can write this expression as AC plus AM1 times cos of omega M1t, because this 2 pi FM1 is equal to omega 1. That means AM1 times cos of omega 1t plus AM2 times cos of omega M2t times cos of omega ct, where this omega c is equal to 2 pi fc. And if we further simplify it, then we can write it as AC times 1 plus mu1 times cos of omega 1t plus mu2 times cos of omega m2t, and further it will get multiplied with the carrier term, that is cos omega ct. So here this mu1 is equal to am1 divided by AC, while this mu2 is equal to am2 divided by AC. So these two are the individual modulation index for the two sinusoidal signals. And if we see the effective modulation index or the total modulation index, then it will be equal to square root of mu1 square plus mu2 square. Or in general, if we have n terms, then the total modulation index will be equal to square root of mu1 square plus mu2 square plus so on plus mu1 square. So in this way, we can find the modulation index for the multitone modulation. Alright, so far whatever discussion we did on the AM, that was in the time domain. Now let us see the frequency spectrum of this AM signal. So let's say this M of f is the frequency spectra of the signal MT. And as we have seen in the previous video, when this message signal gets multiplied with the carrier signal, then its entire spectrum will get shifted to the frequency Fc on the positive side and the minus Fc on the negative side. So basically it is the spectra of the DSBSC signal, right? But in case of this amplitude modulation or the AM, this carrier signal is also sent. So if we see the Fourier transform of this particular term, then it can be given by this expression. That means at the Fc and the minus Fc, we will get the two delta functions. So unlike the DSBSC, here there will be also discrete frequency components at the frequency Fc and the minus Fc. And in fact, that is the only difference between the frequency spectrum of the two modulation schemes. Now if we consider the case of the single tone modulation, then a message signal is a sinusoidal signal of a single frequency. And if we see its Fourier transform, then it will have a two delta functions, which is located at the Fm and the minus Fm. Now when we multiply it with the carrier signal, then this entire spectrum will get shifted to the frequency Fc and the minus Fc. So after the carrier multiplication, we will get the four terms. And here, because of this additional carrier signal, we will also get the delta functions at the frequency Fc and the minus Fc. So this is the frequency spectrum of the amplitude modulated wave in case of the tone modulation. So far we have seen that in case of this amplitude modulation, just by transmitting this carrier signal and ensuring that the modulation index is less than or equal to 1, the demodulation of this AM signal can be made very simple. And because of that, the cost of the receiver can be reduced greatly. But on the other end, we need to pay the price in terms of the total transmitted power. So we will just see that because of this additional carrier term, so much of transmitted power is utilized for transmitting these carrier signals. And in fact, this carrier signal does not carry any information. So that is one disadvantage of this amplitude modulation. And to understand that, let us find the carrier power and the sideband power. And for simplicity, let us take the case of the tone modulation. Now so far we know that for the tone modulation, the modulation index can be given as AM divided by AC. So from this AM can be written as mu times AC, right? And further if we simplify this first term, then we will get the two terms. Now the power of any signal can be given as Vrms square divided by R. That is the power getting dissipated across some load R. So first of all, let us find the power of this carrier term. So for this carrier signal, the RMS value is equal to AC divided by root 2, right? That means the carrier power will be equal to AC divided by root 2 square times 1 by R. Or we can say that it is equal to AC square divided by 2R. So that will be the value of the carrier power. Similarly, let us find the sideband power. Now if you see over here, then the sideband contains the two components. And the RMS value of each component is equal to mu times AC divided by 2 root 2. So the power of each sideband term will be equal to mu square AC square divided by 8RC, right? And since there are two sideband terms, so the total sideband power will get multiplied by the factor of 2. That means the total sideband power will be equal to mu square AC square divided by 4RC. So in this way, we found the carrier power as AC square divided by 2R, while the sideband power as AC square times mu square divided by 4R. And if we write in terms of this carrier power, then it is equal to PC times mu square divided by 2, right? So in case of this amplitude modulation, the total transmitted power, that is PT, is equal to carrier power plus sideband power. That is equal to PC plus PC times mu square divided by 2. Or we can say that it is equal to PC times 1 plus mu square divided by 2. So that is the expression of the total transmitted power in terms of the carrier power. So if we just know the carrier power and if we know the modulation index, then we can find the total transmitted power. Now if we just take the case of the multitone modulation, then for the multitone modulation, the total transmitted power is equal to PC times 1 plus mu1 square divided by 2 plus mu2 square divided by 2. So here this mu1 is equal to AM1 divided by AC, while this mu2 is equal to AM2 divided by AC. So this is the case for the two-tone modulation. But in general, suppose if we have n terms, then the total transmitted power will be equal to PC times 1 plus mu1 square divided by 2 plus mu2 square divided by 2 plus so on plus mu1 square divided by 2. Or we can say that this total transmitted power is equal to Pc times 1 plus mu t square divided by 2, where this mu t is equal to square root of mu1 square plus mu2 square plus so on plus mu n square. And this mu t is the total modulation index. Now in general, for any type of message signal mt, the sideband power will be equal to this mean square value of this m divided by 2r, and the total transmitted power is equal to the carrier power plus the sideband power, that is equal to ac square divided by 2r. So this will be the expression for the total transmitted power. So in this amplitude modulation, since the carrier signal consumes a lot of power, so the overall transmission efficiency will be very low. And this transmission efficiency is the ratio of the useful power to the total transmitted power. So the useful power is the power in the sideband, because the sideband carries the information. So we can say that this transmission efficiency is equal to the power in the sideband divided by sideband power plus carrier power. Now in case of the tone modulation, we know that the sideband power is equal to Pc times mu square divided by 2, while the total power is equal to Pc times 1 plus mu square divided by 2. So if we further simplify it, then we can say that this efficiency is equal to mu square divided by 2 plus mu square. And to find the percentage efficiency, we need to multiply it by the factor of 100. So in this way, we can find the transmission efficiency for the tone modulation. Now if we take the best case, that means when this mu is equal to 1 or the modulation index is equal to 1, then the percentage efficiency will be equal to 33%. So that is the best possible efficiency in case of the AM modulation. Now if this modulation index is less than 1, then the efficiency will further reduce. So as you can see, from the total transmitted power, only a fraction of power is the useful power. That means this modulation scheme is not efficient in terms of the transmitted power. And similar to the DSBSC, this scheme requires the 2 times the bandwidth of the modulating signal. That means if the bandwidth of the message signal is equal to B, then the bandwidth of the modulated signal will be equal to 2B. So we can say that this modulation scheme is also not bandwidth efficient. So in the upcoming videos, we will see some bandwidth efficient schemes like the single sideband and the vestigial sideband. But before that, in the upcoming videos, we will see the different generations and the demodulation techniques for the AM signal. But I hope in this video, you understood the different aspects of the AM signal. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.